They will find us on the way. Don't need to waste time. So who is ready to take over the first part? Number one, A.
Name the first 20 elements in the periodic table using their correct. I had drawn already them.
You drew them?
Yes.
Is it possible to share or?
I don't think so.
It is hard.
Yes.
But you can. You mean you cannot focus your camera there?
Okay. Let me try to send.
Yeah, focus the camera.
So it's only saying the host can share in this meeting.
Yeah. Let me try and see if I can change some. This is shown, eh?
Yes.
Ask to start a video. Okay. As I wait, as we go on. So those ones are very easy. At least we have an idea about them. You can tell us the first 20 elements and their correct symbol.
Okay. Hydrogen symbol H, helium He, lithium Li, beryllium Be, boron B, carbon C, nitrogen N, oxygen O, fluorine F, neon Ne, sodium Na, magnesium Mg, aluminium Al, silicon Si, phosphorus P, sulfur S, chlorine Cl, argon Ar, potassium K, and then chlorine Ca.
The last element is
calcium.
The last element is
Calcium.
shown. The last element is
Calcium.
it's calcium, not chlorine. You have repeated chlorine twice. You have written the correct symbol, but the element you don't
No,
know.
I read it forward.
Okay. That is good. The first work done. Let me share this work. Where is it gone? Draw the periodic table and place them where they belong. Now, those persons shown has already talked about them. Bridget.
Yes.
Bridget, I want you to look at group 4. In your periodic table, do you have group 4?
Yes.
Read for me elements in group 4. If yours is ready, I'm waiting for group 4. What are the elements in group 4? Bridget.
Yes.
Group 4 elements. Read for me if your periodic table is ready. Because this work was for yesterday. Time is going.
Carbon.
Carbon, good.
Silicon.
And silicon. Thank you. Pav,
Yes, teacher.
read for me group 8 elements.
Helium,
Mhm.
neon,
Neon,
and finally argon.
argon. Very good. Dakia, let me hope you got the work. Did you? Hmm?
No.
No. I told you last time. Did you send me your WhatsApp number? Hmm?
Yes. Yes. Yes.
Where did I put the number? Okay. Ruth. Ruth.
Yes, teacher.
Very good. You got the work yesterday, isn't it? Hmm?
Yes.
Read it for me, group 1 elements. Group 1 elements. Mm-hmm. Ruth, time. Group 1 elements, Ruth. Okay, Sean, give me group 2.
Beryllium,
Mm-hmm.
magnesium,
Magnesium,
calcium.
calcium. Good. Somebody give me the ones of group 1.
Hydrogen,
Hydrogen, good.
lithium,
Lithium,
sodium,
sodium,
potassium.
potassium. Okay. Thank you very much. Now people have their predictable. Now these days I will not be talking. When they call me, I just say, Bridget, come and talk on my behalf. Pav, come and talk on my behalf. That's what I'll be saying. Okay. So
Yes.
our next question is here. What can you observe from the periodic table? Let's use groups and the periods. Let's take an example, group 1. What do you observe from group 1? Elements. These are the elements in group 1. Share. These are the group 1 elements. What do you observe from group 1? Yes, somebody is raising their hand. Yes, Sean.
Elements in group 1, all of them have the same number of electrons in the outermost layer.
Same number of electrons. Same number of electrons on the outer shell. That's good observation. Who else? Yes, Pav.
I'm saying that they are having the different atomic structures.
Different atomic structures. Atomic structures. Okay, that is
They have
observation now.
similar chemical properties.
Yes,
They have similar chemical properties.
same chemical properties. Similar
Similar.
chemical properties. Okay, properties. That's another observation somebody has made. Now, when you are going to, let's look at period 2. Period 2. Are we observing period 2?
Yes.
What is the first element in period 2?
Beryllium.
Not
Beryllium.
group, not the group. the period.
Lithium.
It is
Lithium.
lithium, yes. Lithium is the first one. Then the last one,
Neon.
neon. Okay. What do you observe in those elements from lithium to neon? Our hint here was use electronic configuration and the structure to answer this question. So basing on the electronic configuration, what do you see? And then the structure, what do you see? Yes, Sean.
Elements in the period 2, they all have the same number of energy levels.
Same energy levels, yes. Same energy levels. That's a good observation. Who else observed something? Catherine. 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 Okay. Now, when you look at those electrons, the energy levels, what increases on the energy level?
The electrons.
Yes, that's another observation I wanted people to make, that electrons increase. There's an electron increase from left to right. So that is another observation. So we don't want to waste time there. So we have answered this part. Now we are going to question 2. Using electronic structures only, examine the trend as you move from up to down and give your observation. Up to down using electronic structures. What do you observe? If you have drawn the electronic structures, those structures, what do you observe? If you draw from moving up to down, that means if it is up down, those is it the group? We are observing, looking at the groups. What is increasing?
Energy levels.
The energy levels are increasing. That's one. Energy level. Energy level.
Electrons.
Electrons, correct. Is there anything else?
No.
What about atomic size?
It increase.
Atomic size.
Increase.
The size of an atom increases as you go down the group, isn't it?
Yes.
So those are some of the whatever's there. What do you think the electrons on the last shell represent for every member? Group 1, what was increasing? Group 1, the last energy level had how many electrons?
1.
1. Then 2.
2.
What about 8? What about group 8? They are 8. Very good. So our question is saying, what do you think? What do you think the electrons on the last shell represent? What do they represent?
I think it's the valence.
Valency, correct. That's one. Then another one.
The group.
The group, yes. That's good. So people made nice observations. Give a reason to support your answer, especially the group and the valency. For this one, the reason is not common, but at least you see that in every shell that increases, there's only one electron that is left from the last shell. Then that last shell gives you the valency of that element. So the reasoning was not really here so much. So 3 is here. 3 is saying using electronic structures. Using electronic structures. Those electronic structures you have drawn. Only examine the trend as you move from left to right and give your observation. From left to right. I think this one you have made the observation already, isn't it?
Yes.
Yes.
So the observation is increase in
Atomic size.
not atomic size, but increase in
Electron.
left to right, increase in electrons. Good. Okay. Give a reason. That one is not there. But now let's base on atomic size. There are factors we considered when you're looking at this. It is atomic size, number 1. So number 4 is saying, give your idea on atomic size of group 1 elements as one moves from up to down. The atomic size increases, isn't it? From up to down, okay?
Yes.
Atomic size increases, that is good. It increases. Now give your idea on atomic size as one moves from left to right in a period 2. Atomic size as moves from left to right in a period 2. What is your idea on atomic size?
The size is constant.
The size is constant. Huh? That's one observation. The size is constant. Next. Infinix Hot 9. Who is Infinix Hot 9? Infinix, somebody with Infinix is who? Who is that person using Infinix? There's no one using Infinix. I kindly request that person using Infinix Hot 9, you indicate the name, because I don't know who I'm talking to. So remove Infinix Hot 9 and put your correct name. Okay, that is one person. The person has said from left to right, there is increase in atomic size. The size is constant. Who else? Another objectives? I want now people to think properly. The first element in the period 2 is lithium, and lithium is like this. There are 2 periods, and there's 1 electron outside. Then you go to the 1. This is 1. I want to look at 1. I want to look at group 3. I want to look at group 6, and then group 8. 8. 6 is like this. So group 3, we shall have this, and then this. They have 1, 2, 3 electrons outside. Group 6, they have 1, 2, 3, 4, 5, and then 6. Group 8, these ones are full. 1, 2, 3, 4, 5, 6, 7, and 8. Somebody is telling me that the size will be constant for all these elements. Is it true? Okay. Bridget, is it true? Bridget.
Yes.
Is it true? Dakia.
Yes.
Is it true that they'll do this?
I'm not sure.
Huh?
I'm not sure.
You're not sure? This could be Ruth, isn't it? Ruth. Ruth?
Yes.
Uh-huh. We have Ruth somewhere.
With the influence.
Yes, teacher.
Very good. So you tell me, between these ones and this one, is the atomic size going to decrease or increase? Or they are constant? Like other people are saying it is constant.
I think it will increase.
It will increase. Ruth is saying it will increase. Do you have a reason? Huh?
No.
No. But you are saying they will increase. What is the reason? Yeah. Okay. Catherine. Catherine. Suppose she has the whatever problems on the phone. Okay. Now let's look at the trend to which these things behave. In a group 2, in a period 2, I mean, reactions of these things, or the atomic size, the size. Let's look at size. Size will depend on the nucleus. We depend on the nucleus and the electrons on the last shell. The electrons on the last shell. Now, if you want to know that something is small in radius, like this is atomic nucleus, each of the electrons you add on this shell has some force. It is going to impact on the shell. Okay?
Yes.
So the nuclear force of attraction between the nucleus and the last electrons gives us the atomic size of that element. Now imagine there is only one electron like this one on the shell. So it is only one electron pulling some, the force of attraction will be the nucleus and that last shell. That one will be relaxed a little. Now just imagine an atom here. This is the nucleus of that atom, and it has electrons on the outermost shell. And each of them has some force pulling from the center. Will it be small or will it be big? Look at the nucleus and then look at the last electrons on the last shell. Electrons on the last or outer shell. If there are 8 and all the 8 have some force they are impacting at the center, will it be small or big?
Big.
Hmm? Somebody is saying big. Why do you think it's going to be big? The force that is there is the force of attraction, not the force of repulsion. Okay?
Yes.
Yeah, it's going to be a force of attraction, not repulsion. Because if it is repelling, it could be big or something. But if it's the force of attraction, what happens?
It will decrease in size.
It will decrease in size. Very good. So if an electron like this one is on the shell, that means this one is going to be smaller. The smallest is going to be this. Then this one is going to be smaller. And then this one is going to be small. Therefore, this one is going to be what? Big. So when you are moving from left to right in the periodic table, left to right, we shall have a decreasing atomic size. The atomic size is going to be reducing. This one is going to be big. This one is going to be at least smaller than this. This one is smaller than this. This one is the smallest in the whole So group 8 elements, according to the periods, are the smallest. You get it?
Yes.
Because of the nucleus and that attractive force between the nucleus and the last electron. You remember that every electron you put on the shell has some force it impacts on that atom, the nucleus of the atom, because it is the nucleus where you get the protons and the neutrons. So all those protons, when they remove or when they want to become ions, they become charged. So this is what happens. Each of that element will have some force it will impact on the nucleus, meaning this one is going to be small than this one. This one is going to be the biggest in the hollow period. Okay? So that is the trend we are observing from left to right. Now, what about when you are coming down? When you are coming down, we see atomic size is increasing. So from the top, this one is small, increase in every shell. The shell increases the size of the atom. So this one is going to be increase from up to down. So there is a general increase in electronic shell from up to down, but from left to right, there is a decreasing. The whatevers remain the same. The size of an atom, okay, the nucleus and the number of shells. The shells remain the same. The shells are the same in the given period, but because of the number of electrons increasing on every shell, that increase will force the whatevers to be small. Have you understood?
Yes.
Good. That's a good one now. So if you look at, that's one, atomic size. We have looked at atomic size. Atomic size. Now I want us to generate our own, what we call a reactivity series of elements. Reactivity series of elements. Let's start with one, metals in the periodic table. When you look at metals in the periodic table, those ones in group 1, do you think if you look at group 1, we have a general increase in atomic size, isn't it?
Yes.
Now, when that size increases, when the size increases in group 1, my phone is just here moving up and down and it's not giving me clear pictures. Okay. So in group 1, if you look at metals indirectly, we have the first metal as, is it hydrogen or lithium? First metal in group 1, is it hydrogen or lithium? Is hydrogen a metal?
No.
No. Hydrogen is a gas. We have seen from many reactions that hydrogen is a gas. So the first metal is lithium. We come to sodium, and then we go to
Potassium.
potassium. Now, when you look at the big periodic table, the big one, let me, if I can try to get it. If you look at the periodic table, let me pick one that is clear. Now, do you see this table clearly? Where are the group 1s? They are all covered. This one is not good. Is this one clear now?
Yes.
So you see here, you see lithium, you see sodium, you see
Sodium.
potassium. Now there is this RB, there is RB, then there is CS, then there is F what?
FR.
FR. For us, we study only up to here, the first 20 elements. First 20 elements. but the rest are down. This is rubidium. Rubidium is here. Rubidium. This is cesium. Cesium. And then fragium. Those are the elements lastly in that what. So the periodic table is as big as this. It doesn't stop here, but for us, we're only interested in this. Now, if you look at this is in a period 2. It has 2 electron shells. These ones have 3. 1, 2, 3. These ones have 4. 1, 2, 3, and then 4. Now, this one, if you look at metals, we looked at them as elements that react by, is it loss or gain? How do metals react? They react by losing or gaining.
Lose or gain.
Metals do one. They either gain or lose. So which one is that?
Gaining.
They react by gaining, isn't it?
Yes.
So
Yes.
there is some echo I feel on the ground. Who is echoing? Okay. In simple terms, metals react by losing electrons. There is some echo I feel on the ground. Who is echoing? So when metals react, they lose electrons. So for them to react like those ones of group 1, they lose only 1 electron and they attain the stable state of the other element that is before it. So if sodium loses electrons, it attains the stable structure of 2 to 8. 2 to 8 is a structure of 2 to 8 is a structure of what? 2 to 8 is a structure of neon, isn't it? Yes?
It's neon.
Very good. So the trend is like this. For metals, since they react by losing, now when this lithium is as small as this is the nucleus. This is the last electron on the shell, this one. Now, this one, since the distance between this and this, the force of attraction holding this electron between the force of attraction between the nucleus and the electron is so strong, Now, if it is strong, this electron cannot be lost easily because of that small atomic radius. But now when you look at something like potassium has 4 shells. The first one, the second one, the third one, and then the fourth one. This is the nucleus. This is the last electron here. The force of attraction between the electron and the nucleus, and you're not seeing, this is what I'm trying to demonstrate, that the force of attraction between the nucleus and the last electron